Hi everyone, this is Maria and we're going to be talking about polarity. So we're going to talk about what polarity actually means and then how to figure out if a bond's polar or how to figure out if a molecule is polar. So starting with polarity, it's really describing the idea that valence electrons are being shared unequally in a positive bond or in a polar bond or in a polar molecule. So what that actually kind of spells out is there's this slight positive charge on one atom or on an area of the molecule if we're talking about molecules, and then a slight negative charge on the other atom or area or areas of the molecule. So water is a wonderful example of a polar molecule. We're going to look at the electrostatic potential maps because that often helps us kind of just visualize the fact that there's positive and negative areas. So knowing that the positive areas are blue and the negative areas are red, we can see pretty clearly that the hydrogens have more positive charge around them. And then if we're talking about the oxygen, there's more negative charge around it. So water is a great example of a polar molecule. Let me show you a great example of a nonpolar molecule. So this one is completely nonpolar. You'll notice when we go through and look at some of these electrostatic potential maps that not all of them look quite as simple as this one. But because we often find nitrogen triply bonded to another nitrogen atom, this is what the electrostatic potential map looks like for nitrogen. So you can see that it's completely gray. It's very, very neutral. So it doesn't have those stronger positive and negative areas on this particular molecule. So first, let's talk about how you determined if bonds are polar. So you start with an electronegativity difference between the two atoms. The difference is always going to be either 0 or positive. If you have a negative difference, just take the absolute value. All right, so you go through and do that. Here's our general range that we've talked about in class. So 0 to 0.5 would be a nonpolar bond. 0.5 to 1.5, then it'd be polar. And then anything over 1.5 would say ionic. So just remembering that this means that the bond is not actually covalent at this point. Nonpolar and polar bonds are both types of covalent bonds. And then please remember, these are just general guidelines. Polarity is on a spectrum. You will see all sorts of different values on the internet when you're looking up different charts here. And people kind of base what would be considered a nonpolar bond or a polar bond kind of around specific bond types. You don't have to worry about that, though. You can just use these. We use these numbers because it's pretty easy to remember. So let's just do a quick example. So if I'm looking at the nitrogen and bonded to fluorine, well, if I look at my periodic table, I see fluorine's 4, nitrogen's 3. So we get this difference of 1. Well, that falls into our polar bond category. So just for some practice, I'd pause this right here. See if you can go through and categorize each of these different bonds. All right. So I gave what the difference in electronegativity is and then what each of those would be considered according to the values that I presented over here. Okay, so let's go ahead and talk about molecules. How would you determine if a molecule is polar? The very first question you should ask yourself is, are there any polar bonds in the molecule? If the answer is no, you've already got a non-polar molecule. Cool, you're done. You don't need to do anything else from that. The answer is yes, there are polar bonds in the molecule. You have to ask yourself, is the molecule completely symmetrical in 3D space? I'll explain what I mean by completely symmetrical in 3D space in a second. But for right now, let's kind of consider the yeses and no. So if it is a completely symmetrical molecule, the answer to this is yes, that's a non-polar molecule. If it's not completely symmetrical, the answer is no to this question, then it would be polar. I would copy this down and include this in your notes if you don't have it down somewhere already. Again, I do want to remind you, polarity is on a spectrum. I can describe one molecule as more polar than another molecule. We'll take a look at this when going through. We can also describe things as more nonpolar than another molecule. We're kind of trying to turn something that has a lot of shades of gray into a black and white issue. And so just always keep that in your mind when going through. So what do I actually mean by symmetry? So we've learned before there's things that are symmetrical and there's the things that are asymmetrical. For this particular one, it's symmetrical just along the y-axis. And this would be considered asymmetrical along the y-axis. Well, as I said before, we need to consider the 3D shape of the molecule. It's not quite as simple as before. So we're always going to go through and think about it on the x, the y, and the z axes before we declare something completely symmetrical. I'll show you what I mean when going through, but it's this idea that carbon dioxide is a completely symmetrical molecule versus water, which we already know is a very polar molecule. Water itself is an asymmetrical molecule. So just keep that in mind. I know this has the words dipole moment and bond dipoles. You don't really need to worry about those very much. So I just like this visual. Okay, for these examples, what I'm going to suggest is that you pause at this point in each video and go ahead and draw the Lewis structure. So for the Lewis structure for this one, go ahead and it should look something like this. The molecule, or the way that I'm visualizing these molecules is unfortunately doesn't actually show the lone pairs. So I'll just tell you about them every single time. There are 2 sets of lone pairs on this one, so you'd get them on the oxygen here. So there'd be 2 sets of lone pairs on oxygen. All right. So remember the first question we always ask ourselves, are there any polar bonds? The answer, yes. Although hydrogen to carbon is not a polar bond, carbon to oxygen definitely is. And so the answer is yes. So we got to ask ourselves the next question. Is this a symmetrical molecule? Well, it is certainly symmetrical along the y-axis, but once I try out the x-axis, it's not. And so, just to kind of further give evidence for what I'm telling you, this is what the electrostatic potential map looks like. You see, it's not quite as blue and not quite as red as water was, but it's reasonably blue and reasonably red in the different areas. I can see that when I go through and just take a look again at the symmetrical, like the axes, again, the y-axis, it's completely symmetrical here, but once I look along the x-axis, this would no longer be symmetrical. And as I said, it's confirmed by the electrostatic potential map that we're looking at. Okay, so this just sort of sums up what I was saying. So it's definitely a polar molecule because we've got that polar bond in there, that carbon-oxygen, and then it is an asymmetrical molecule. So both of those things together give me polar molecule. All right, let's look at the next example. So carbon dioxide. So pause here, draw the Lewis structure for carbon dioxide. Okay, carbon dioxide should look something like this. You would also need to have 2 lone pairs on each of the oxygens. So there should be 2 lone pairs there, 2 lone pairs there when you're looking at carbon dioxide. Okay, so we actually already talked about the carbon-oxygen bond. That is, in fact, a polar bond. So let me move on to the next question. Is this completely symmetrical in 3D space? Well, if I look on the x-axis, sure. If I look on the y-axis, sure. The z-axis is trickier. Remember, that means that it would be going into the computer and then coming out of the computer when you're watching this, or out of the screen, whatever you're watching this on. And this is pretty confirmed by the electrostatic potential map. Now you'll notice there's this is not as perfect as our N2 molecule that we looked at earlier. There's slight areas of red and slight areas of blue. But overall, this would be considered a non-polar molecule. You won't ever have this, right? When looking at this on your Lewis structures, you'll just have your Lewis structure. But this is just, again, a helpful way of sort of visualizing. This is something that's maybe not completely non-polar, but if on the spectrum of things, if I'm looking at nonpolar versus polar, this would be considered nonpolar. Okay, just keep that in mind. And again, we can take a look at the symmetry. So along the y-axis, yep, same on both sides. X-axis, same on both sides. And then z-axis, which I've drawn as a diagonal here, that is in fact coming out of your screen and back into your screen. It's also symmetrical along that axis. So, because even though there's polar bonds in this molecule, it's completely symmetrical in 3D space, this would be considered nonpolar. This is just sort of a quick summary of what I just talked about. And let's go on to example 3. So let's look at BH3. Go ahead, pause, and draw BH3. Okay, now that you've drawn it, remembering that BH3 for boron, it's an octet exception. It's only got 6 valence electrons that it needs in order to fill its outer valence shell. Remember the first question we always ask ourselves, are there polar bonds? Well, the answer is no, there is not any polar bonds here. This is a difference of 0.1, not a polar bond. And because of that, that means automatically this is a nonpolar molecule. This is again very confirmed by the electrostatic potential. Only the teeniest hints of blue and red when going through, and so therefore this would be a nonpolar molecule. All right, let's look at example 4. I'm going to own right up that it is a tricky one. So go ahead, pause, draw the Lewis structure for HCN, so hydrogen cyanide. And then, so here's the structure. Remember that there's a lone pair on the nitrogen as well, and that's just something to help keep in mind. All right, so remember, we got to consider, are there polar bonds here? Now, if we are being really, really like strict about our guidelines, technically, we know already that H to C is 0.4. That's under our nonpolar. But if we're looking the C to N, it's at 0.5. Okay, so remembering that there's a lone pair on the nitrogen, that kind of pushes us more towards it's slightly polar. It's a slightly polar bond. As I said, this is tricky. But so in that case, we do actually have to consider the symmetry of this molecule. So let's go ahead. So along the x-axis, totally fine. But once I switch to the y-axis, no longer symmetrical. And that's again confirmed by the electrostatic potential. Pretty blue, pretty red. And so when I'm looking at this, again, just kind of going over those planes of symmetry in my mind, I'm fine on the x-axis, not so fine on the y-axis. So just something to consider when going through these molecules. So this would be in fact considered polar. Not incredibly polar, but polar nonetheless. All right, this just sort of sums up again part of what I was saying. Okay, so let's go ahead and take a look at just certain sort of shapes are more likely to be polar. I'm not promising you that they're always polar, but they're more likely to be polar. If you want, you can pause and just think about which ones you think might be more likely to be polar, but this would be the answer. So ones that have a lone pair on the center atom are more likely to be polar. You can also have these other shapes be polar as well, especially if the X atoms are not the same. That definitely means that they're more likely to be polar, but just something to consider going through. All right, well, so this is your question to try at the bottom. Draw the Lewis structure of SO2. I will say that getting the connect the dots method might be really tricky to use for this one, so just consider that when going through. Then you want to go ahead and identify the electronic and molecular geometry, and then think about, is it more polar or more of a non-polar molecule? So consider all of that when going through. All right, your teacher will go over this question with you in class, so make sure you write down any questions that you have. All right, have a good night, and we will see you soon.